All right. Oh, yeah. And before we pick up on the lecture, let's just remember about the final. We got final info page, tells us when it is, topics and things. It'll be on the 20th, which is the Wednesday of finals week, in this room, same time as class starts, but a little less than normal class time because it's just time to take the test. So we'll have that. And yeah, let's get back into the lecture stuff. So remember, classification is just the idea of predicting a categorical variable. We don't predict a number like, okay, this is 1.75. This with these inputs, I want to produce 2. I think the answer is 2. Classification is a categorical thing. So like a spam filter, spam or not spam, those aren't numbers, right? Cars and roads and things, those are categorical things and not numbers either. So self-driving cars, AI umpires, fun examples, plenty of things. A classifier is just something that you wrote, you trained it in some way, and you give some attributes, some things that you want to use to make predictions, maybe the height of the mother, the height of the father, or a bunch of different information about a blood test, and the predicted label is like height of the child, or whether or not we think you have this specific kind of disease, stuff like that. All right, so we learned a lot about a specific kind of classifier. It was the nearest neighbor classifier. It was like, all right, you give me all this data on these blood samples. I'll go and plot that data in a potentially very highly dimensional space. And I'll go find the closest things that I know about in my training set, right, because we snipped it up. I'll go find the closest things that I know about and maybe the closest 5 things, and I'll look at their labels because I know information about people in my data set. I know what if they had the disease and if they didn't. And this person that I don't know something about, but I know their blood test stuff, I'm trying to make a prediction as to whether they have this disease. I know all this other stuff. I can see how similar they are to people in my existing training set. And that's what you do. You go and find that, and you count how many people close by that person in terms of their readings. Have the disease and don't have the disease. And if you use an odd number of people, you can have the majority rule, right? And so that was the nearest neighbor classifier, the K nearest neighbor classifier. You pick a K, you go plot your new person in a potentially highly dimensional space. You find the distance from that person to everybody else. You find the closest K things, and you look at their labels. Got two blue and 1 green, which means we will predict for this person that they are blue. Yeah, that was K nearest neighbors in a nutshell. And we had a bunch of cool examples about that, and we practiced with it last time. And I want to show you that K nearest neighbors isn't the only answer, right? K nearest neighbors is not the only answer. We just gave a hint at this last time. But if you want to make predictions based on like categorical things, K nearest neighbors is the one thing I showed you. But we also use nearest neighbor to predict numerical things. We also used it to predict numerical things like the height of a child, right? You go and you find all of the points that are nearby. Do I have that at the start of this? I do not. We did it from like last chapter, right? When we were learning linear regression, it was something, probably chapter 15 then. Yeah, we did this. We found the closest people within a range, and we used that to predict. That was also nearest neighbor. Like, all right, you give me a height 70 child, or we know the average of the parents' heights was 70. We go around like half an inch, and we average together all the people we know in our training set, right? And we use that to make a prediction as to how tall this new child might be. That's still nearest neighbors. You're going to the nearest people, the nearest dots, and finding stuff, but it was just one or two dimensional, depending on how you think about it. You can do, and then we learned about linear regression to predict numbers, right? Still, by finding the best line through all this data, we can do the same for a bunch of numbers predicting a third number, one last number. Okay, so cool. We know about linear regression. That's predicting a slope and an intercept to get the best line through all this data that we have, and we can use that to make predictions. You give me somebody new with this x value. Oh, why does the pen never work when I get in here? Because I was using rainbow to make a point here. Well, I'll use blue again. Like you get somebody new with this value, and you find the best line through your training data, and you can predict this, right? So that's numerical prediction now. Numerical prediction now. And that was trying to learn the graph of a line to make some predictions. You give me this input, I'll give you this output. if we have a bunch of input data, like all these different readings for blood samples and things, and we're trying to predict a numerical value, then we could do the same game but in higher dimensions. All right, it's a little weird looking if you've never seen this before, but you can imagine that like there's an equation for something like a line in 3 dimensions, and that's called a plane. It's like a little flat thing, kind of looks like a line. And you can use that to predict new values. If you have a linear relationship in higher dimensions, it'll look like something like that. And my example here is going to be house prices. So you give me like the square footage of the house, how many bathrooms does it have, all these numerical quantities about a house. We can use that to predict how much we think it'll sell for. And so you give a bunch of different inputs, not just one, but a bunch of different inputs. And we'll predict slopes, which is kind of like the relative importance of each of those things. And then we will output how much we think it should sell for. And so that is our goal right now. We would like to do not just linear regression with a single variable, it's called multiple linear regression. We have multiple input variables still producing one output, the price of a house. But let me show that to you because it makes more sense with words. All right, this is called multiple regression. And let me show you what I mean. I'm going to need to scroll down. So this is where we left off. So this is using kind of a bunch of numerical inputs like we were doing for k nearest neighbors, but not to predict a categorical thing anymore, now to predict a number. Right? So it's regression again, it's multiple regression. Multiple linear regression. And then just remember that regression in general, it's just a generic idea, it's the generic term that means to like make a prediction that turns into a numerical answer. That means to predict a numerical variable. So we did nearest neighbors for regression. That was a type of regression. We also did linear regression to draw a line. Okay, so here's some house data. I think, where did it sell for? I forget what city that they stole this house data for, but they made a data set, the people who made the textbook, they made a data set of a bunch of people selling their houses in, why do I think it was the Midwest? I'm not sure, but a while back. It's called house.csv. And this is like a bunch of sales for houses, all sales we'll call it. All right, and this is the data set. Got a bunch of different inputs and all these different values, like did they have a fence or not? What kind of fence was it? But there's a lot of numerical pieces of this, like basement square footage. What else do we have? The year that it was built. That's a number, right? That's a number. How many stories? Square footage of the living room, all that fun stuff. How many bathrooms, how many kitchens, because apparently you can have more than one kitchen. How many rooms were in the house? How many fireplaces? So a lot of these houses have 2 fireplaces. Crazy. When was the garage built? Like all these numbers. And let's use a few of them, all right, to make some predictions. So I'm just going to steal this from this because I want to filter out some of these things. Like a lot of these things are not even numerical. So here's what I'm going to do. I'm going to make a table called sales based on that, where we're going to have single family houses only, not like places where like you can't buy it. I don't want to like think about buying an apartment complex for myself or something like that. And then we're going to go to sale condition normal, not like it's not a foreclosure or something, and we're going to pick out these numerical values. Sale price, square footage of the first floor, square footage of the second floor, square footage of the basement, area of the garage, I guess also in square feet, why they call it area, I don't know. If there was a wooden deck in the backyard, how big was it? The porch, how big was that? The area of the lot entirely, the year that this thing was built, the year that this thing was sold, and last sold at least because they're trying to sell it now. And yeah, we're sorting it by sale price. So this is like the cheapest house, had some very small square footage, and was built very long ago. And then like you see like, okay, this one was sold for a little bit more because it was built a little bit later. stuff like that. Maybe it was in a different area. This one was sold for more because it had a second floor. So you can kind of see what's going on there. And so let's take a look at like all these different houses that were sold. Let's explore the data. Sales histogram, sale price, Benz equals 32. And then the unit is in dollars, money. Oh, excuse me, what have I done? Sorry, it's unit is the variable. So here, sale price of houses. And it looks like in this city at this time, the houses were trying to go in for a little, about 150,000 each time they sold it. Okay. Yeah. So this may be something that we can predict, right? We have this data set. We got all these numbers. We would really like to take all this data. How many of these are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 attributes. All these things except for the sale price. Use them to predict the sale price of the house. All right. And we might be able to get away with linear regression, multiple linear regression, and predicting these kinds of slopes for this hyperplane thing, magical, if it turns out that this graph is kind of linear. So let's pick out some of these variables like the first floor square footage and the sale price, because we want to predict the sale price, right? So sales.scatter. Let's do the first floor square footage. We want to use that to predict the selling price of the house. This would just be normal linear regression if we only use this single variable, but we'd like to use all of them because like you get more data, right? If you have the second floor square footage, like that gives you a better idea of what the price should be. And you see this is kind of linear, right? If you have more room in the house, then it's going to go for more money, right? Smaller houses are going to sell for less, but it kind of explodes. It's like a megaphone almost. Because it's not a perfect predictor, right? You know that a very tiny house in San Francisco or Santa Cruz is going to sell for millions of dollars, whereas a very large house in Fresno might go for a few $100,000, right? That's the thing. So it's not the first floor square footage that's going to tell you the price. It's a combination of things, right? So let's look at like the correlations of some of these things, because like this is decently linear, and so like that's maybe your first step. You'd notice that okay, we've got some linear stuff going on here. Let's bring in our correlation functions because we need that to find the correlation of something we need to convert to standard units. So here, correlation between sale price and first floor square footage is like 0.65. That's decently correlated. All right. So if we use just the sale price, or sorry, just the first floor square footage to predict the price, we would, I mean, we're not horribly inaccurate. It's decently correlated, but you see that we would make some like, we'd be inaccurate trying to draw a line through all that. It wouldn't be perfectly accurate, especially for the higher square footages. So idea, right? We've got all this other data too, the second floor square footage, the garage area. Like let's use all of them at once to make the predictions, just like we did for K nearest neighbors, except it's not a categorical thing. It's not like did it sell or did it not sell. It is now the actual sell price. So that's a numerical quantity. So idea, we could use all. Let's just use all the numerical attributes that we have to predict the sale price. That would be great because the more data, the better, right? You have more accuracy. That would, if you used all those variables all at once, that would probably correlate even better. And that's our goal. All right, enter the idea of multiple linear regression. Multiple linear regression. So we're using multiple variables. We're trying to draw the best line in this multi-dimensional space through it, which is just kind of the idea. Instead of finding a single slope at an intercept, finding a bunch of slopes. Like you think of them as like the relative weight. Like, okay, the first floor square footage had carried this much weight in the sale price. The second floor square footage will find this variable, carried this much weight in the sale price. The basement square footage carried this much weight in the sale price. And you add it all up, it turns into a number that we think it might sell for. Okay, let's do the correlation of everybody. Let's find the correlation of all these different variables, because like all at once, I'm sure first floor square footage has that by itself has the highest correlation to sale price, but like taken together, maybe we can do even better. So let's find the correlation just of each of these variables by themselves to sale price. So if we do that for label and sales.label, because if you go to the sale, right, the sales table, we know all of the labels that we could find things in, and this is something that we can go, this is like an array. So we can go through it for every label, and this labels, think of it like an array. It's not quite an array. let's call a correlation on that label, on the sales table, on that label that we're looking at right now to the sale price. And then we'll print it all out. So let's make it pretty. So print the correlation of this label, whatever it was, and sale price, colon space, is whatever this is. So it's trying everybody. Correlation of sale price and sale price, of course, 1.0. But look at all these other ones. Apparently garage area and sale price correlates well. Basement square footage correlates the best, apparently. That's nice. Year built, the later it was built, probably it's going to sell for more. So that also makes sense. But like the best that we got here is 0.65 correlation. 0.65. That's not great. I mean, it's not horrible, but it's also not great. You see that like we'd have some error if we draw the best line through this graph. But if we combined, right? If we combine some of this data, like first floor square footage, maybe plus second floor square footage, right? That's the square footage of both of the floors. Maybe we get an even better number, right? That's something that's a combined value, right? So like what's the correlation between like the area of both floors? Let's calculate that first of all. The area of both floors is first floor square footage plus second floor square footage. So sales dot column, what was it? Sales price was 1. So 0, 1, and 2. Columns 1 and 2 together. Let's add them up. Column 1. Oh, why can't I click right now? Oh, there it goes. Column 1 plus sales dot column 2. This is just me adding up the area of both of those floors. First floor square footage plus second floor square footage, making a third thing that is both of them together, like a big variable. What about the correlation of those? So correlation of sales, I guess I've got to add it, right? Sales dot with a column. Let's add both floors so I can talk about it. That's like this. So now I've produced this thing, right? First floor plus second floor. Here I've got both floors over here on the right as another variable. Now we can do the correlation of this table with sale price to both floors. That new thing that I just added. What's its correlation? Do you see that? We get 0.7. That's better than any of those individual ones together, right? Any of those individual ones. We took two things and suddenly we've got a better predictor. Yeah. So that's pretty nice. It's better than just one. We'd probably have a better, tighter line. We get a better prediction if we use both floors together. And so kind of, I've added them up. It's kind of hinting at this process, right? If I add up every of them and like weight them appropriately, it's better to combine these attributes together, right? So it's better. It's more accurate in a prediction. It correlates better. It's better to, linearly correlates better as well. It's better to combine multiple attributes. So let's try to combine them all, right? That is our goal. So now we're going to find some combination. Oops. We're going to find some combination of all these different variables. First floor square footage, second floor, garage, year built, and learn. We're going to learn the best weights for each of them. Those are slopes in this multi-dimensional space. We're going to draw some sort of line-looking thing in like a 9-dimensional space. There's 9 variables that predicts sale price, that turns into a number that is our sale price. Okay, that's our goal. So we want to learn this. All right, we want to learn this. Let's see. How do I want to do this? Yeah. So we got the housing prices data set. This is multiple linear regression because there's multiple variables involved to predict this last final variable. And we want to predict the house price given all the other data on the houses. All right, does that make enough sense? What we're trying to do, we're trying to learn these slopes to predict this number. You could also like add in your intercept, add a third thing, but we don't actually need it for this one. We'll get accurate enough. So that's pretty cool. Yeah, are we ready? Because we want to train this. We want to do the same kind of process. It's still kind of like a prediction engine where we want to make sure we're not messing anything up. So we're going to cut it up and make sure we're not memorizing things either, right? So we're going to have a training set and a test set as well. So let's get that going. So sale, how many, we gotta chop it up. How many rows we got? 2,002 rows. That actually chops up cleanly. in twos, but usually people don't cut their training sets and their test set exactly in half. Usually use more for training and then less for tests. So let's do like, I don't know. You can cut it up into threes if you want. You can cut it up into fours. You can use like 3/4, a quarter. But you know what? Let's just do half each time. It's fine. But let me show you something. If you wanted to cut it up into like 2/3 for this one, 1/3 for this one, you can't really do it kind of the way you want to. But let's chop it up first, and I'll show you what I meant. So if I want to train and test, right? I want a training set and a test set. Let's do equal halves. Again, I don't want to take it in the order that this was in, because this is like probably like it was compiled in some order that like is logical, maybe like by streets or something. And so there's probably some, it's not perfectly random if I take the first half of this data set and the second half. Like I want a perfectly random test set and a training set. So I'm going to shuffle it first, right? So sales, I do a sample of everything without replacement. Then, now I've shuffled all these rows, but I still have just as many. And that's my shuffled sales table. And so taking from that now, my training set can be the first half of that, so shuffled sales. So what's half of 2002? It's 1001, right? It's like take up to index 1000 for the first one and be the A range. But you could have done it like this. It'd be like 2002 sales.numRows divided by 2, because that would give you up to index 1001, right? And then test could be take that thing and start from that, right? Onwards to the end, sales.numRows. Do you see what that would do? It's like it's going to calculate the first half of the stuff by calculating this index. So take up to index 1001, and then from 1001 on to the end, the last index is numRows. I guess I need numRows. Yeah, that would be the last index that doesn't exist, 2002. So it goes from index 0 to 2001, right? So 2002 is like the one you don't want to get to at the end. You see that kind of process would like cut it in half, and I don't need to know what indices to care about. So that would be nice, but it doesn't work, sadly. It would work if I actually typed go up to 1001, like do the math myself, 1001, 1001, go to 2002, like that would work, but it would be nice to do it the other way, right? To be like, hey, instead of this, let's just calculate it. Sales numRows divided by 2, because maybe you got more data, like this would be very easy, right? Sales numRows, like that would be nice to have it calculate that, but for some reason we get this big error, and the issue is with types, sadly. The issue is with types. This won't work because slash produces a float. So sad. All right. So look at what happens when I do sales numRows divided by 2. I don't get something that could be an index. I don't get 1001. I get 1001.0. All right. This is a kind of an aside, but this is going to like get rid of, or this is going to make sure that there is maybe like a 0.5 involved. Because what if you wanted to do divided by 3 where you don't have an actual index? There would be that involved, right? There would be decimals. And so division may produce decimals. So division in Python will always give you back a number with decimals. But we want to use indices, right? There is no index 667.333, right? On forever. So what are we to do? There's a secret in Python where if you do 2 slashes, it will produce an integer. So by 2, it produces the actual 1001 that you can use as an index. If you do 2 slashes for division by 3, is it going to round it? Like we'll figure out what happens. It just chops off the decimal places. It's like it makes an int by doing it the easiest way possible, just getting rid of any potential decimal places. And so if I want to use this method of like automatically calculating my my training set and my test set by calculating the indices to stop at, I need to use the double slash because that will produce an integer. All right. I hope that made a little bit of sense. That's kind of beside the point, but that will give me a training set and a test set. It will work, and they're going to each have the same amount of like rows. So, because I did it divide by 2. And it happened to be perfectly the same size. But if I did it by 3, numRows, test.numRows. It might take a little bit more if you do it by 3s, right? Or a little bit less because it's going to do that rounding. Like this one's 667. This one is like it rounded it up or down, depending on how you think about it. So, okay, we got 2 pieces. I've automatically generated, I've figured out the indices to do this with. So I've cut up my test set into, or my sales data into a training set and a test set after I have shuffled it. All right, this is like the automatic process. Thank you. So you can kind of make a function if you want to, like chop my data set in half, please, by just like giving the name of the thing, because that's the only difference, right? You got shuffle a thing called sales, and then you divide by 2 with 2 slashes. It will always work. Okay, so now our goal is we want to find a bunch of slopes. We want to find a bunch of slopes for each of these variables, like the square footage of the first floor times the slope, second floor square footage times the slope, garage square footage times the slope, year built times the slope. We want to learn these numbers to predict the sale price most accurately. And so our goal, find a bunch of slopes. And make a prediction, right? So if we had a bunch, if somebody gave us, some magical fairy gave us a bunch of slopes, here's how we would use those slopes to make this prediction, right? You take let's make a function called predict. If somebody actually found the slopes for us, what would we do with them? We'd use them with the inputs, right? We'd multiply the first slope times the first input, second slope times the second input, all day long. You add them up, right? That's all you do. Somebody gave me 9 slopes. Here are the slopes as an array of them, and you give me a row of data, right? A row of data with all of its first floor square footage, second floor square footage, blah, blah, blah. Here's what I would do to do that prediction. I'd take the slopes, I'd multiply it by the row as an array, and then I just add them up. Call sum on that and return it. So kind of slopes is, let's make a doc string for once. So slopes is the array of all the slopes that we want to use. Like somebody magically generated them for me. Is the array of like M1, M2, M3. So somebody gives me that, and then also row. Row is the X1, X2, X3. You give me those 2, as many as you need, and then here's what I'll do with them. I'll do M1 times X1 plus M2 times X2 plus M3 times X2 all day long. Right? That's what I'll do, and that's how you calculate, right? And so if somebody gave me the slopes, here's how I would use it. So like you give me a row that you want to predict for, or you give me some sort of house that you want to predict for. So like test dot row 0. But we don't want to use the sale price, right? We're trying to predict the sale price. So let's drop the sale price. So here's like a row. Like you have this data on this house, but we don't know the sale price. Let's try to predict it, right? So this is my example row. If somebody gave me slopes, here's what we could do. Let me generate a bunch of random slopes. You don't have to understand what I'm trying to do. A bunch of slopes normally distributed from 1 to 10, kind of, just as many as there are in the example row. This will generate a random array of a bunch of numbers that are normally distributed, around 10 as the mean with standard deviation 1, just for fun. So these are some example slopes. I'm just generating randomly a bunch of as many numbers as there were. So like this is pretend. Let's pretend these were the good slopes that give us predictions. This is as many, because we want as many slopes as there are x values. So I've just made some example slopes. So if somebody gave me a row they want to make a prediction for, and these were the good slopes that a magical fairy came up with to do predictions with, then I just kind of want to take that, multiply it by that, take that, multiply it by that, add them together. All right, so run this function. So here's how the function would act on that. Be like predict with example slopes. That was the first thing. Then example row. That was the second thing. And apparently it would predict as this, but that's probably a horrible prediction because these slopes are just randomly generated. I have no clue what the actual thing is, but we know that the sale price of the row 0, the actual row 0, item 0. This was the real sale price. Actually, not that far off, surprisingly. Nice. Some of these random slopes worked for this first house, but they probably don't work for every other house, right? So that's what we want. We want to learn even better slopes that give you a better even more accurate answer. Here, let me get some new random slopes because if I did this again, see, it's even farther off now. So not the same. So that's great. And I've got all these training rows. Where am I? I got all these training rows, and now I've got all these test rows. So we're going to use the training rows to find the best slopes for this training set. And we're going to try to see if we didn't just memorize something, and we're going to use the test set, okay? That's our goal. So does everybody understand what we're about to do right now? We're going to learn the best slopes to predict the sale price for the training data. And then we're going to see how accurate it was for the test set that we saved away, that we didn't do anything with yet. We didn't look at it. We covered it up. Any questions about that before I do it? Oops. Dun, dun, dun. So yeah, let's give it a try. That's my training data right now. You would have a different one if you did it randomly. So let's figure this out. So here are my attributes, right? My attributes that I want to do training on is I want to use everything but the sale price, right, to predict the sale price. So my attributes, as I'm training things, I'm training my regression engine. It's just like my training set dropped column 0, which was the sale price. Don't look at that. And then the prices that I'm trying to generate from those attributes, each of them, the prices, that is column 0. So this first variable is everything but column 0, and this last variable is column 0. So here's everything. Like I've got an array of every single row right now in train attributes, and then I've got a table of every row. And then train prices is the column, the array of all the prices for each thing, and they're just lined up, okay? So what I'd like to do is I'd like to find the best slopes that predict the sale price. You remember how we did that, like how we defined that for linear regression? It was the best value that kind of minimized something. Remember what that something was? Started with an R. It was a weird acronym. But that's what gave us the correlation value. The reason that we chose those equations was it minimized something called root mean squared error. Remember that? That's the word. We can do that again. We can minimize the root mean square error of making slopes to predict sale prices. It's just more things involved, but that's fine. All right, so root mean squared. We want to do that for multiple linear regression. That's what we're about to find. So goal. We're going to make a function that, like, you give me what you think the best slopes are. I will tell you how far off they are. I'll tell you the root mean square error of using those slopes to make a prediction. All right? We want to minimize the function I'm about to write to find the best slopes. Because we got a minimize function in our library. So here, def, RMSE for root mean square error. So you give me the slopes that you think are good. You give me the attributes that you're trying to figure out the best slopes for, the attributes that you're going to multiply and add to the slopes, and you give me the actual prices, the actual variable that you're using the slopes with the attributes to predict, and I'll tell you how far off you were. All right? And the way we're going to see it, we're going to calculate is the root mean square error. So we're going to calculate all the errors at once. So the errors, let's make an empty array, and we'll add to it each time, because it's like for each of these attributes, right? It's a different row of them, right? It's a different row of them. So it's a different house. We're trying to find the error for that house, find the error for that house, using these slopes that you give me. All right. So let's go through all of them. So for I in np dot a range, let's get all of the possible indices of all the different rows. So you can do len prices. So that's one of the ways. So you can also do attributes num rows. Either way. So these are all the indices of all of the different things. Like I've got 1001 attributes and 1001 prices. That's what it's going to end up being. So this is going to be I between 0 and 1000 then to do all those 1001 things. So every time I got a value for I, I've got a row I can look at and make a prediction for. So what is the row right now? It's attributes.row I. The price of that house. So this is a house right now. This is one of the houses I want to make a prediction for using these slopes, right? Here's the real price that it sold for, actual price. Just go to the same place of that array, because like attributes row 1 is this thing, right? Everything but the sale price. And then trade prices, right? Prices row or item 1 is also this one because they went in order. Okay, so that's the sale price of that house. And the predicted price is us using the slopes and the attributes together, right? The predicted price is, all right, we made this predict function to do that. So you give me the slopes. So here, we're pretending we have them. Predict. So here's the slopes that you thought were really good. Here are the attributes for this one row. Here's the row you're making a prediction for using the slopes. So that's the predicted price. And we want to see how far off was it from the actual price. So the root mean square error for that is, so what was the error itself? Boop. We have the actual price minus the predicted price. That was our error, right? It's actual minus what you predicted always. Though we are going to square things, so don't worry about that too much. But that's one of the errors. That's how far off we were for that one house. So let's add that to our array of errors. Does it make sense what I've done? Like I'm going through all of these, like you give me a bunch of attributes and prices, one for each house, so they're in lockstep. I'm gonna go through each one of those, each one of those houses, see its actual price, predict the price given the slope that you give to me, the slopes that you think are best. Here's the predicted price based on those slopes. Here's how far off your estimate was, because it'll never be perfect. And then I'm going to keep track of all of them. And then we want the root mean square of all of those errors. All right. So I've built up a bunch of errors in this array. And what do I want to do with it? I want to, so it's a root mean square error, right? So it's backwards. The first thing we do is we square the errors. Errors squared. As the squared errors, then we want the mean squared errors, right? So we're going to do np.mean. I want the root mean square errors. So you take all those mean square errors and you square root them. You read it backwards. And that is the root mean square error of using these slopes to predict the prices of these particular houses. We're using this data to predict these prices. So you hide them for a second. All right. Are there any questions about that? You see how that's going to calculate the root mean square error for this data set using some slopes that you've given to me. It's like we can use our example slopes that are not good right now. We're going to find some better ones, but for those example slopes, our training attributes, our training prices, apparently this is how far off we are. We are on average off by, for this definition of off by, root mean square error is off by about $80,000. So that's a decently large error because some of these prices are like a couple $100,000 only. So that's a decently large error right now. So our random slopes are not great. But remember what we have. Train attributes and train prices are, the attributes are all these things. Here, let me separate that real quick. So that's train attributes. It's like train attributes looks like this. It's this table of everything but the sale price, and then train prices is that array of all those prices. All right, so that's what I have right now. So I'm using all these, this row, trying to predict this data. Using this row and slopes to predict this sale price for that house. So that's what we did. And we found that we were off by that much for our random slopes. But we'd like to give, we'd really like to find the best possible slopes, right? We don't know what the slopes are that we should have. The ones that will minimize the error predicted in the sale price. But we got a function for that, right? So let's make a function that we can give to this minimize idea. Remember what that does, by the way. There it is. So minimize takes a function, and it gives you the inputs to that function, like if this was a function. It gives you the inputs to that function that would give you the smallest answer. So that's exactly what we want here, right? We want to give it like a function that takes some slopes and finds the root mean squared error for those slopes to make a prediction on our training set. And we want to find the smallest inputs, so the smallest answer, right? We want to find the best slopes that give us the smallest error. So let's make a function that we can give to it. So def let's make a training function. So like RMSE took more things, attributes and prices. We just need a function that takes only the slopes. We'll make RMSE train. So we're going to train our predictor to minimize the root mean squared error. So you give me some slopes, and then I'll return back to you the root mean square error of using those slopes to try to predict house prices using our training set. So train attributes, train prices. And so if we call it on our example slopes again, we're off by that same amount, but I can minimize this now. I can minimize this function so it will find the inputs, find the best slopes that give me the smallest output for the root mean square error. All right, so if I say minimize RMSE train, and the way that we're going to use minimize is a fancy way. So minimize takes a few options here, and we're going to use some of them. So because we have a bunch of things involved. Usually it can figure it out when you have like just one input or two inputs. This is like, we got like 9 inputs now. There's 9 different slopes we're trying to solve for. So the way that we're going to use minimize, and again, you don't have to memorize this or anything. This is just like what we need for this purpose. We're going to minimize this function, RMSE train, that calculates the root mean square error for some slopes that you give to me for predicting house prices. And then we'll say start. You got to give it a starting point. Like this is our guess for where the slopes might be. They're not very good, but our example slopes. We'll start there. And I have to say smooth equals true. So it's not a jagged function. It's not wonky going up and down. It's like smooth. It's supposed to be a line-like thing. And it is an array. Our input is an array of things. You need to solve for an array, please. The best slopes will become, it takes a second to think about it. It's going to find and try to discover the best input. And it really does take some thought. But once it's done, we have some good slopes for our data set. All right, now some good slopes for our data set. And then I can show you what's going to happen. All right, I'll tell you what the slopes are. But it's very possible that my starting point was a bad starting point. It took too long. Okay, but no, it found it. It found some good numbers, and here are what the numbers mean. They are the it's like what you could put next to the first floor square footage, second floor square footage, all that stuff. Like what you could put next to those. So table. Let me put it together. Train attributes dot label. Again, don't worry about what I'm doing here. I'm just trying to put it next to the same things. Labels with a row that is best slopes. And that's what I want. Cool. So this is what it found. It found that the best slope for this first floor square footage, like it contributed 72. That's $72 per square feet. The second floor square footage, if there was one more square footage for the second floor, it made the house price increase $74. Does that make sense? That's what we discovered. And if you had one more square foot in a basement versus another house, for every square foot in a basement, it's worth about $50, we discovered. Garage is about $60. A deck is about $30. Everybody has a porch, so like you have a bigger porch, only $2 extra apparently. The area of the lot itself contributes, like for every bigger square foot for the lot itself, you get 50 cents. That doesn't really matter because you could have like a big lot but a tiny house or something. The year built is very important. Apparently, for it was built 1 year later, it's worth about $500 more, which kind of makes sense, right? And then the year sold, the year it was last sold, is apparently a negative thing. Like if it was sold more recently, in this data set at least, that means it was worth, like if it was sold a year more recent than another house, it was worth $500-ish less dollars. Which also might make sense because people like to, the more people have moved into that house, kind of the more beat up the house is, maybe. You can think of it that way. Like that's kind of what we've discovered. And so like you want to buy it from the original owner who's been in there for a while. It was sold long ago. So that's kind of neat to discover that. So that's what we found. All right. And so let's find, let's see what we found here. Let's see what the root mean square error of those using those slopes is, right? So what was the root mean square error for these slopes, best slopes? For our training set, it was about, on average, $30,000 off versus our random slopes that was about $80,000 off. So yeah, you give me these numbers for the basements and the square footages and things. We'll give you a price that's about accurate for our training set. That's like within $30,000 of how much the house should sell for. That's decently accurate, right? That's pretty cool. So we've got a test set, right? Way back up here. We've got a test set still. We've got a test that we haven't looked at. Let's see how accurate we were for the test set. We got a function that does it all. So test attributes. So first of all, the test set is all this stuff. So sale price and the attributes we got to split up again. So it's test attributes now. It's test drop column 0. Test prices is only column 0. So there's those things, and we can do the root mean square error for the best slopes here, and I think that's what I want. RMSE for the best slopes, using those on the tests now, on the test set. How far off are we on the test set? Did we just memorize the training set? This is the question now. We're about as far off as we were for the test set as we were for the training set. So that means we kind of learned what it means for a house to cost money. That's really exciting. And this is our root mean square error for multiple linear regression. So this is a linear root mean square error. We're about, on average for our test set even, $31,000 off. That's a decent predictor of a house price. That's so cool. That's really cool. So like, I don't know, here's our test set, row 0. Sale price of this, all these values. Here's what we predicted it to be. It was predict with our best slopes test.row 0, or test attributes. We predicted that house to be, we predicted that house to cost, instead of $167,000, like $180,000, so about $10,000 off, which is decently close. That's pretty cool. All right, so yeah, let's see how accurate we were for each of the houses, right? So let's generate the our prediction for each of the houses in like our, which data set? Do we want to use the whole thing? Let's in our test set, let's say. All right. So let's do that. Let's for our test data, for our test set, let's add a column called our prediction, or it's like our fitted data, right? Our fitted prediction. That's what we use for linear regression. So fitted is, let's make a function, I guess, that we could apply to this row that does it right. So def fit on row. Let's return the our prediction for that row. Let's see. Yeah, it's really just predict using our best slopes, that row. So I want to apply that function kind of to our data set. So test dot everything but the sale price. So drop 0 dot apply fit. I think should work. We'll find out. Does that do it? So here it is. Now here's our prediction for each of those houses' prices. Cool. So that's there, and we could plot that now. So let's call this something. We can do a scatter plot with the fitted data and sale price. How far off are we? This is how far off we were. A perfect line, right, would be the right price. So sale price, if it was $100,000, we should have fit it for $100,000. We should have predicted $100,000. Let me show you what that means. So PLT, let me plot a line. Y equals X line. Don't worry about this. 0, 5, 85, apparently. If we were perfectly accurate, our prediction would be exactly the same as the sale price of that house. And we're decently close to that one. That's not bad. We're off by about $30,000 on average, but that's how good we did. And we could, just like for normal regression, we could do a residual plot. We could be like, we can calculate residuals, and let me just copy and paste that one because you kind of understand the idea. It's going to look like that. And again, you kind of think about residuals as it was the error of your prediction. How far off was the thing? And so it looks like we are decently, like it is a jumbled mess. It is just a blob. So you're looking for blobs, right? To mean that it was linear. It was decently accurate for houses that weren't super duper expensive, but you see, like we weren't too off below or too off above. But do you see how as the houses get more expensive, we were always underestimating their price? See that? That's the idea. So for the most expensive houses, always above that line, which is that means nonlinearity. So that means that there's something else about those houses. Maybe they were like antique houses. Maybe there was something special about where they were located. Like all that just is showing that our data wasn't perfect. It was not a linear relationship for super expensive houses, but for like generic houses within a normal range of prices, we got it accurately. We were predicting it decently accurately with no like, weren't too far above, too far below. Okay, so we're underestimating the price of the most expensive houses. But we do pretty well on the majority of them, which is great. It's exciting. Yeah. So that is a process. That is us trying to find the best slopes to draw a special multi-dimensional line to predict our houses. But it's also like a weight. Like how heavy weighted, how important was the first floor square footage? How important was the second floor square footage in the final price? That's pretty neat that we were able to calculate that and use functions that we knew about from before to make that happen. So that was kind of like a line, so they call it multiple linear regression. Multiple variables involved, not just one. Not like y equals mx plus b anymore, but like a bunch of different x's. Cool. Any questions about multiple linear regression? It's pretty neat. That's one way to predict numerical variables from a bunch of data at once. But you better believe we also could have done what we've done before. You could use k-nearest neighbors. You could use some amount of nearest neighbors for multiple regression. So for example, what we could do, we could use multiple regression is just the idea of predicting a number. Multiple linear regression is predicting this kind of line-based thing with all these slopes, but we can do k-nearest neighbors for regression as well. So if k is 5, for example, like here's our house data in its multidimensional space, right? Here's our house data. Let's say we have a new house on the market. We want to estimate how much we think it's going to sell for. We plot it, right? It's like, this is our new house. Oops, I want a different color. This is our new house. And so maybe if k is 5, go and find the closest 5 houses to this house in this space, like that one and that one, maybe that one. Oh, this is hard. I drew this bad. Which one's closer?
The one that's right on the bone, you sure?
Let me just erase that one. There. These are the closest 5, right? And we know all these guys, right? We know this one's price that it sold for, this one's price that it sold for. All these other people, we know their prices that they sold for because we have that in our data set. Just average them, right? They were the closest 5 houses that were similar in attributes. Go average their sale prices. Use that as our prediction of this new house's sale price. That's honestly easier to think about than the other one. But it's a different way, right? A different way of predicting things. So I guess your k doesn't have to be odd this time. It doesn't really matter anymore. Just like take a few houses that are close by. But same idea. Does that make sense? Now we're predicting a number now, not like looking at labels. We're looking at their sale price and averaging them up. Okay, that's pretty neat. So let me show that to you in our remaining time. Nearest neighbors again. Another way to do multiple regression. Regression, predicting a numerical variable. Multiple means for a bunch of data, for a bunch of attributes, not just one. Nearest neighbors to the rescue. So it's another way of doing this. Nearest neighbors for regression. Boop. So okay, let's just use a few of our. We do have training data and test data already. Let's use, just to make this go faster. Apparently, this is what your textbook did. They're like, we don't care about the index 5, 0, 1, 2, 3, 4. So they don't care about the wood deck because it's usually 0. So I'm going to select out just a few of the things that we care about. Train neural network, train.select 0, 1, 2, 3, 4, and 8 were apparently the ones that they cared about. So we're just taking a few of the most highly correlated attributes to make this process value, because it took a while to run minimize, right? Taking just a few. We're going to do something similar. It's going to take a while if I don't get rid of some of this stuff. So just the highly correlated things. If you had more time, just give them all. We'll take just a few, though. Speed things up. Less things to look at. And then we'll do the same for my test set. Take the test set and select out only those columns as well. That's our test set. Just give me those. That's a train. Just a couple of them. We're just taking the first floor square footage, second floor square footage, basement, garage area, and year built. Those are the highest correlated things. We'll use those to predict the sale price. All right, so it's just a 5-dimensional space that we're going to plot these things in, which is making it a bit easier. All right, so let me show you that. Scrolling. Yeah. Again, you can do all this yourself, but I have copied and pasted it. So here's a bunch of things from before, like our distance function, right? Let's do a distance function that give me 2 rows. I'll give you the distance between those 2 rows of the table. That's, you got to turn them both into NP arrays first, right? This function gives you distances from, oh gosh, compute the distance from example. So you have somebody you're trying to predict for, right? You want to see how far off this new point is from everybody in your data set, all right? And we're going to exclude, we're going to say output means our sale price. We're going to make sure to not include that one because that's not part of the attribute. So we're going to exclude our output label, which is our sale price that we're trying to predict. So that's what distances does. And here's kind of we're getting close to nearest neighbors. Like for the trading set, for this new point that you care about, to predict this output variable, take the k closest things. Go find all the k closest things. So like, all right, get the distances, sort by the distance, take the top k. So like all these functions you can think about and you can figure that out, right? And so let's for this example row, let's look at it real quick. So like here's one of the rows of the data set, right? We want to use this row, these attributes, to predict. We want to find the closest 5, let's say, things in our training set to this input. And it looks like these are the closest 5, right? These are the closest 5 in that data set. All right. So that's the idea. And yeah, that is they're these many distances away. And what we'd like to do for these like 5 things that look a lot like the original house. Let's keep both of these actually. So like for this house in our test set, here are the closest 5 houses in the training set to that house in terms of those attributes. And let's make a prediction, right? We want to predict based on like average up their sale prices, right? Because they're the ones I know about. So what I'd like to do is let's make a function that is called, gosh, do I want to type this out? Should be fine. I'll type it up. So I want to predict using nearest neighbors. You give me this new point, which we're calling example. Give me some new point, example point, and give me a k value, which we can have default to 5. And what I want to do is return the majority among the k nearest neighbors, the majority value, right? Or not the majority. We want to average together, right? Average together the sale price column, right, for each of these examples. Average together the outputs column values for the k nearest neighbors. And that is our goal. That's kind of what we want here. That's our prediction. So how do we do it? Well, we'll call this closest function, right? Call the closest function for our training set on this example row. K equals whatever we gave. We're using it to predict sale price. And we're going to the sale price column. So we got the top K, top 5, let's say. Go to the sale price column for our predicted value, or for our closest things. Go to that sale price column. And then just average them all up, right? We can do dot mean, I think would work. And return that. Does that make sense? That just goes and it finds the closest k things using one of those functions, and it's going to average these together and use that to predict the price of that house. So we call it predict nearest neighbors on my example nearest neighbors row. What do we got? It's apparently predicting it to be this much money. It's going to cost this much. And here I made a little, let's print out both of the things we care about together. Here's the actual price of that test house. It was 167,000-ish. And our predicted price using nearest neighbors was almost that. That's even better than our multiple linear regression prediction, most likely. That's crazy. So what we'd like to do is see, like, all right, for this data set, for these houses, would it be better, because we did find a linear relationship, would it be better to use multiple linear regression to predict house prices, or would it be better to use k nearest neighbors to predict house prices? Because either one, right, will give you a prediction. Which one's better for this data set? It's not necessarily the case that it's like one's always better than the other. So here, let's do that. Boop. Here, I'll just copy and paste because like this code makes sense if you look at it for a while. There's a lot of it though, I know. So here's what we're gonna do. Let's make, for everybody in the test data set, we are going to make predictions using k nearest neighbors. We're going to call this predict function on everybody, right? Make some predictions for my test set, right? And we're going to calculate the root mean square error for the test set by calculating the errors, right? Root mean square error. So errors, square it next, then it's mean, then it's root. So you read it backwards, right? That's the root mean square error for using nearest neighbors. And we also had the root mean square error for doing the predictions for multiple linear regression. And so once I run this, we're going to do it for the other one, and we're going to see who wins. Was it better to do multiple linear regression, or was it better to do nearest neighbors for house price predictions? And this is going to take a second because this predict function, we're calling it on 1,000 rows. It would have taken even longer if I included every single column. So it's going to take a second, but we can print out the residuals. I'll get that ready to go as well. It's like residuals. Boop. We'll predict that as well, or we'll look at that too. How far off is it for the house prices? So yeah, this is like, it's really crunching the numbers. Now it's doing this for everybody. So it looks like for nearest neighbors with k equals 5 at least, that was our default, it is actually a little worse. For multiple linear regression, it was off by about $31,000 for every house. And for nearest neighbor, it looked like that one that I showed you was a lucky house. It looks like on average, it's off by about $32,000, $33,000, unfortunately. So it looks like multiple linear regression is the winner right now. It looks like we also have the same kind of residual graph where we're decently accurate. It's like a little blob for normally priced houses. But as houses got more expensive, there was something else driving the price, like probably location, probably like schools and things like that. And so for the more expensive houses, we were always underestimating their price, even with this different kind of prediction. And so that means that maybe you want to cut it off at like, all right, for the normally priced houses, for like average houses in the neighborhood, this is a good predictor, but you'd want to predict it in a different way for the more expensive houses. Okay, so that's pretty neat, and that's good to know. We could potentially do better, though. All right, so first of all, do we understand what we're doing? I think conceptually the idea kind of makes sense because I can draw it very easily. Like for k nearest neighbors for multiple regression, you just go find the closest k houses, average together their sale price. There's your prediction, right? Didn't matter that it was like a 5-dimensional space or something. It didn't matter. Just like go find the ones. We have a distance function that covers that. Okay. One thing I do want to say is some attributes are more important than others, and units kind of ruin things. So let me show that to you. So here, sometimes in our data set, we have attributes that are on completely different scales. Like think a serial data set, right? Some of the things were in milligrams, some of the things were in normal grams, and some things were in cups and stuff like that. And so the numbers were way different. Same for the chronic kidney disease data set, all right? So they're on like completely different scales, and that kind of ruins distances, right? That kind of ruins the distance calculations. So if you can imagine, look what's happening. Do you see how, like, if I wanted to know how far apart, like for distance-wise stuff, how far apart was this row from this row? Like you do some calculate, like, okay, it's this many, like you do the subtraction on each of the things. Subtract those, subtract those, subtract those, add them up, take squares and square root, right? That was our distance calculation. Do you see how these values are really far? They're 6,000 apart, whereas these values are like 3 or 40 apart, yeah? When it came to a distance calculation, kind of these values don't even matter. You're going to be picking up this giant distance for these giant units. Does that make sense? That's not very useful. That's not very useful. The distance of these two rows is going to pretty much be this difference because these values are so close to one another. Like this was a huge distance, and it's just going to use the white blood cell count really to tell you how far apart these points were, when in reality, we want each of these each of these columns to carry equal weight, right? We want the glucose just to be just as important as white blood cell count. We'd like these values to be similar. I guess one thing you could do is like divide them by 100 to get the decimal places in a normal place or something. I don't know. But an even better idea would be to convert each of these columns to standard units. Because you know that for normally distributed things, and usually most values are, or even if they're not normal, it still applies, right? Everything is more or less, the values are between like -3, like a z-score of -3 to the z-score of +3. Standard 3 standard deviations below the mean to 3 standard deviations above the mean. Like every value is going to be between -3 and +3. They're going to be on an even playing field. That's the whole idea of standard units. That would make each of these values be on an even playing field with one another. And so you wouldn't have this situation where the white blood cell count is kind of like the star of the show. It would take over for these other distances. Does that make sense? Like, it didn't matter what the glucose and the hemoglobin, like these values for the distance calculation, because what's going to happen, right, for the distance calculation for those points is going to be like, all right, it's the square root of 117 minus 70 for those guys, distance between those 2 points, right, squared, plus 11.2 minus 9.5 squared, plus 6,700 minus 12100 squared. Like that's the distance between those 2 points, right? And this is going to be a giant number, and these are kind of useless. They're going to not have equal weight. If we wanted them to have equal weight, we could turn them into standard units. And then these values would be nice and small. These values would also be like, they'll all be between -3 and +3. And nobody would be more important than anybody else. Okay? Does that make sense? Any questions about that idea? That would give us a better prediction, maybe. Okay? So let's go back to the chronic kidney disease data set, and I'll just copy and paste this stuff just to show you what's about to happen. But I want to do chronic kidney disease, because we did that once already, right? CKD using standard units. Let's see. Did we do it without that already? I think we did. Yeah. So here, let's if I scroll back up, where's my CKD stuff? Here we did it. We did it before for CKD, and we did the it's been a while, right? My nearest neighbors, CKD on Alice, all distances, CKD. Where was our evaluate accuracy function? There it was. Was this for? No, this was for wine. Sorry. I guess we don't actually know what would have happened for the other one, but that's okay. Let's use standard units. We can discover the difference later. But this is going to make things more accurate, I would say. All right. So let me show that to you. So I'm going to import all the things that we need because I don't want to go find each individual function all over again. So let's do, this is k-nearest neighbors for classification again. We have that evaluate accuracy function as well. What we're going to do is we can turn things into standard units if we need to. So here, let's go back to our CKD data set. I'll just copy and paste it again. All right, here's our CKD data set. We've got all these values, hemoglobin, glucose. Let's use white blood cell count as well this time. We actually didn't use that last time, did we? And let's try to evaluate the accuracy of using this data set, right, to predict stuff. let's see. I want to do both. Like I want to show you the error. I want to show you the accuracy of each of these. So let's see. Yeah, maybe. No, we'll do it with the original one in just a second. But here, let's convert each of these to standard units. So here's my original CKD table. How many rows are in it? Because we also want to evaluate stuff. We want to predict. So 158 rows. I would really like to split this up into a training set and a test set again. So all right, divide it by 2, right? Divide it by 2. To get an index to use, I can do a double slash to get an integer value. So 79 would be my thing. So shuffled. I gotta shuffle it first. .ckd.sample with replacement equals false. So I've shuffled them. Now let's get a training set and a test set. Training set equals shuffled ckd. You can say .take 79 if you wanted to, or take np.arange 79. So take the first 79 things, half and half, and then the test set. Remember that you could have done the test set. You could have done the same thing, but you could have had Python take care of what is this value. You could have just been ckd numbers over 2. Take from there on to the end, ckd.numbers. That's another way to do it. All right. And so I made this function that evaluates the accuracy of the training set and the test set. But let's actually, before we get there, let's turn these tables into, let's turn this table into standard units. Okay. So above all this, let's get a standard units function going, and then I'll convert it. Boop. So here, standard units, let's apply standard units to my CKD table. All right. So here, instead of normal hemoglobin, take the original column for hemoglobin, convert it to standard units. Remember what that is. Distance away in terms of standard deviations away from the mean. Got that function. Glucose, turn it into the standard units version of that column. White blood cell count, turn into the standard units of that column. Class, just keep that along for the ride. So now instead of this, all these values, see how widely different they are. Look at white blood cell count especially. If I go down to here, do you see how all these values are now finally on an even playing field? All right, white blood cell count, whatever it was about half a standard deviation below for this first one, rather than a giant number that has 6,000. All these numbers are between -3 and +3 for the most part. And so they all have equal weight. Apparently this was a very important one. There's a very high white blood cell count for this one, and you can see that based on the distance away from the mean. That's really nice and useful. Okay. So now we can let's turn this version of the data set. It's called CKD again. Let's turn that into our test set. So still, we've got the same number of rows, but we can shuffle it, and we can evaluate our accuracy of using these values to predict the class. Class 1, class 0, right? So we got that evaluate accuracy function that does this entire process of nearest neighbor. So you give me a training set, you give me a test set, you give me what K you're using, and it will figure this all out. So from stuff that we had before, I just copy that back in. So use the training set, shuffled, right? And we split it up half and half, and these are also in standard units now for everybody. Training set, test set to test with, and let's do K equals 5. It looks like we were about 98, almost 99% accurate using standard units, right? Making every column on an even playing field. We're able to say, okay, yeah, this person had CKD, this person didn't have CKD, because if I took a sample. We also have zeros and ones in here, of course, right? So yeah, that's how that works. That's really nice. That's good to know. And we had decent accuracy for this particular split for training and test. If I had a different training test split, I get a different accuracy, of course. It learns different things, but that's pretty close, all right? So last step, let's see how good we did. Let's compare this, right? Let's compare this to if we just left it alone, right? If we just left it alone and used this giant white blood cell count values, right? If we just left it alone, let's do the same thing. Let's go back, read it all in, right? Go back, read it all in. And honestly, let me have you try it. So this is what we're about to do. Let's compare, right? Let's compare the accuracy against the original units. And so maybe That can be a little subheading or something. I don't know. So here's the original table again. White blood cell count. These weird values. Maybe you should. Let me have you try this. So let me give you all this code. I'll give you a few minutes. You just call evaluate accuracy, really. But let me have you copy and paste things in for a second. So here, let me give you everything that we've done. And we'll talk about what you can try right now. If you would like to refresh the code from class, you should now have everything we did today. And so what I'd like you to try to do is get that CKD data set, read this one in just like we did here, use these lines to read it in. This is the original data set without any converting to standard units, and just do exactly what we did. Again, get a training set, get a test set for this version of the data set, right? Shuffle it, get things without standard units, get a training set and a test set without standard units, and try to evaluate its accuracy using this function, right? So just like copy and paste all of this and call evaluate accuracy on a training set and a test set that you came up with from this version of the table. And we'll see how far off it was. Like this one was 97% accurate. Let's see if it's not going to be as good because it's really just going to be looking at white blood cell count as we found if we didn't do that conversion. So see how bad it is. See how far off it is if we didn't do that conversion to standard units, right? Give that a try. Let me know if you have any questions. So you'll have to ckd.csv. But I'm interested. So almost 98% accuracy for the first one, which is insanely good to predict whether or not somebody had this disease. If we forgot about doing that, we're definitely going to get a worse number. Definitely going to get a worse number for how accurate this data could predict chronic kidney disease. And that's not good because like you want to use this in a doctor's office. You want this to be as accurate as possible. And so you want every single column to have equal weight. And standard units are a great way to do that. So yeah, try to do the process, and then I'll walk us through. It's just going to be that we're going to call evaluate accuracy after we make a training set and a test set. So it's a lot of copying and pasting, but you got to remember which things to copy and paste. Why do you need to do that? I did that. Interesting. One thing that could be fun is to play around with the split. Like we just kept doing half and half splits. You don't have to do that. You can do like 3/4, 1/4 split. Usually it's the training set that's bigger. But you know that if you had more training data, you'd probably predict things better. You'd learn more. So that's the age-old question. How much do you use? How much? I guess the correct answer is to always get more data if you can. But that is expensive. That comes with a cost for sure. Yeah, I'll give you another minute to try. I will need to do that. But we're going to be pretty shocked, I hope, if you've gotten it to work. It's going to be a stark difference. Oh, it catches me off guard. All right. Any questions about like what we do? It's really just you call this again. Kind of do this process all over again, but with the same data, different kind of data set, right? So it honestly is going to be copy and paste all of this. So here we've got, we called it CKD again. That was nice of us. So we do the same exact thing. Boop. We call evaluate accuracy. Boop. 76% accurate versus 97% accurate if we convert it to standard units. That's insane. So you should always be converting standard units if we can. If you see, unless your numbers are on the same like level, like if every number was like in milligrams or something, then it is the same units are fine. Unless those numbers are like wildly different amounts, it's hard to justify not putting things into standard units. All right, so this makes things better and more useful, and this will save us when we're doing a distance calculation. When we're doing a distance calculation, this will put things on an even playing field. It won't make things like these 2 points, their distance really depending on one variable more than others. All right, and that would also help us with prediction. Right, it would also help us with the prediction of a house price. If you turned all those attributes, everything but the sale price, into standard units, again, the distance between the houses wouldn't depend as much on like first floor square footage versus porch square footage, because porches are always going to be smaller than the square footage of the whole house, right? Nobody has a porch that's the same area as their house. So like put them on an equal playing field. That might help you with the prediction here as well. Might give you a better root mean square error. So honestly, maybe try that. That would be a great exercise. Try to convert the attributes for houses into standard units and see if you get a better root mean square error for doing k-nearest neighbors regression. That's cool. It didn't actually matter to convert to standard units for this one because we used the minimize function to find the best slopes for those particular units anyway. That one didn't matter. But for everybody else, for distance calculations, that's going to throw them off, right? And nearest neighbors was doing distance calculations. Okay, that's kind of weird, but also good to know about. So yeah, that's the moral of that story. And that was honestly everything that I wanted to write in code for this chapter. Does this last bit make sense? Any questions about any of that? Because you should pat yourself on the back. This is like as far as we go into the idea of machine learning in this class, and I know that's a buzzword that's exciting. Like this is the start of like learning how to make an AI chatbot. Like you would eventually learn enough to be able to do that. This is the start of that. All right. So all AI is, it's just a fancy buzzword that's using machine learning to do some sort of specialized prediction, like text, like generate an image, stuff like that. And machine learning is just statistics, and data science, is just a buzzword for statistics plus computer science. It's just a bunch of marketing and buzzwords. You know those ideas, right? You're learning the basics of those ideas in this class, and that's really exciting, right? It's not a lot of a difference to learn how to make a prediction engine that's not quite nearest neighbors. There's a way to make it like a little, it's called a neural network. It models a virtual brain and things like that. Like that's not a big jump to learning about that stuff is what I want to say, which is nice. Yeah, that's good for you. If you went into a data science degree at a 4-year college, or if you went into a computer science degree at a 4-year college, you'd have the opportunity to take a machine learning class, and you would see that like the first bit of the class is going to be all this stuff. It's going to be this kind of like, okay, let's do nearest neighbors, let's do multiple linear regression, and then you start building on top of that a little bit more. So that would be the next steps. That would be one of the next classes that you would take at a 4-year college on a data science degree path, which is really cool. All right, so pat yourself on the back. You know some basic machine learning now, because k-nearest neighbors is a legitimate machine learning algorithm that people use to make predictions, and you can see that like it's helping doctors. Like these are data sets with real world data, and you can tell somebody if based on like their readings from their blood tests whether or not they have this chronic kidney disease, and that is going to save lives. And that's really powerful and really cool, right? I think it's hard to not motivate this chapter. It's a really good chapter of the book. Okay, I think that's most of what I wanted to say for the day. I have some more stuff to talk about, but that's beside the point. And everything that I talked about up until now is Project 3 stuff. So like we've already assigned, that's good to go. So yeah, I think the last thing is just to make sure we're good. We're going to come back, and there's one more chapter in the book. Like I have a little bit about something outside of the book. I want to talk about ethics. We'll get to that, but that'll be a problem for next time. And then I'll talk about the last chapter of the book on Wednesday, and that's going to be exciting. But this is the second to last chapter. It's probably the most involved. So definitely start Project 3 early if you haven't already, because it's like everything's going to be due. It's next week, right? That's the last week of classes, and yeah, then we got the final. So just make sure you got you understand how time is flowing. One more week of classes where you come to class, and then week 18 is finals week, and so you'll eventually come on our day and you'll take the final. The Monday, because we don't have a final on Monday, there is nothing on Monday for this class during finals week. Right? It's just the one that you show up on Wednesday only. Okay? Just want to make sure we're all on the same page about that. And I'll talk about like late assignments and stuff next week. But yeah, I think that's all that I wanted to say. Let me stop the recording.